Good morning, ladies and gentlemen, invited guests, respected dignitaries, and all other participants. Today, we have gathered here for the fourth technical session of ongoing national conference DEEP 2022, hosted by Elite College of Engineering. Technical session 4 is on mechanical engineering and is going to be moderated by me, Professor Dipasri Shaha. Mr. Jeet Vishwas and Professor Gautam Das are the web hosts of current session. Professor Dr. Bimangati Gupta, Senior Professor and Head of the Department of our college, is the session chair of this session. Honorable Judges are Dr. Subhashish Banerjee, ex-principal of Elite College of Engineering, and Dr. Ashwini Kumar Sharma, former Dean Adamas University. In this session, we have also a keynote lecture by renowned Professor Dr. Pramod Kumar Patwari. Before Sir starts his session, let me introduce him in this platform. Dr. Pramod Kumar Patwari is a professor in Department of Mechanical Engineering in National Institute of Technology, NIT Silchar, Assam. He has joined NIT Silchar as faculty member in the year of 1995. He obtained his BTech degree in Mechanical Engineering from Neris Titanagar, ME in Production Engineering from Jadavpur University, Kolkata, and PhD from the Indian Institute of Technology, that is IIT Kharagpur. His major areas of research include advanced or non-traditional machining, micro-manufacturing, and computer-aided manufacturing. He has published around 50 papers in international journals, around 65 papers in international and national conferences. He has published around 20 books and book chapters. He has supervised 8 PhD scholars and 31 MTech students. He, along with his students, filed 3 patents, and out of which 1 patent is granted. He has also 3 projects in his credit, including one under DST FIST program. Currently, he is the life member of professional bodies like Indian Society for Technical Education, the Institution of Engineers India, and Institute of Smart Structures and Systems. Once again, I welcome you all to this technical session, and I would like to request the audience to put your queries or views in the chat box, and it will be clarified at the end of this lecture. Or you can raise your hands for your queries at the end of this keynote lecture. I feel privileged to invite Dr. Patwari sir to please start the session on joining of materials for consolidated products. Over to you, sir. Thank you. Sir, you are not audible.
Thank you, madam.
Thank you. It's okay now, sir.
Uh,
You may proceed.
Thank you for this introduction and giving me an opportunity to deliver a lecture in this forum. So, at first, I am very much thankful to the entire fraternity of Allied College of Engineering, Kolkata, and especially Professor Sudeep Basak, who has invited me in this conference, that is a national conference on development in engineering education and practices, the DEEP 2022. I am really grateful to all of you, and I am again very much thankful to all the participants who are sitting here in this conference hall to hear me, maybe virtually. So, to start with, I share my slides. I have shared my slide. Please respond whether it is visible
Yes,
to
sir.
you or
Yes, sir.
not.
It is perfectly visible.
It's visible. So that's fine.
Yes, sir.
So to start with, the title of my today's presentation or talk is Joining of Materials for Consolidated Products. I am Professor P.K. Patwari in the Department of Mechanical Engineering, NIT Silchar, Assam. To start with, let us see a glimpse of, or you can see a bird eye view of NIT Silchar. This is the campus, lively campus, green campus of NIT Silchar, and it is spread around over 600 acres of land amidst the green tea gardens in and around. And in our campus itself, you can see many water bodies and so much of flora and fauna are there. So in this picture, you can see this is our main administrative building. This is the guest house. This is the guest house, and here is the mechanical engineering department here, and this is the hostel area, and here you can see the faculty quarters and some more merit scholar hostel and all. So in this area, our campus is spreaded. Now, about NIT Silchar, if I say that it is 48th rank in engineering in NIRF 2020-21 and 93 third in overall category. And it has got many rankings in national and international level. These are some glimpses of NIT Silchar. So you can see the infrastructure of NIT Silchar, and it has got many modern laboratories in the department with modern equipments and all, and a very good nice library that we say that Bharat Ratna Dr. APJ Abdul Kalam Learning and Resource Center. This is the front view of one of our mechanical engineering building, but it is well spread with 3 or 4 buildings. It is only one that the first building where the offices and all are there mostly. And these are some of the equipments in the laboratories where I am connected. This is that laboratories are advanced manufacturing laboratory or micro nano manufacturing laboratory. So this is a brief about the institute and the department. Now I am coming to the topic. So the topic was the joining of materials for consolidated products. So first of all, let us try to see what is a consolidated product. If we look around, we'll find that the most of the products which use right from the morning to the night or in every day-to-day life always. So most of the products are consolidated products. And how these I can say is how this is a consolidated product, because mostly they are assembled by combining a number of components. So you can see the computer in front of that you are sitting, or the mobile you are using, or even the pen you are using, or the day-to-day life, all the components, even the vehicle by which you are traveling, that is also a consolidated product. So that is the importance of consolidation and that the assembly, so that you can use the product in a very effective way. Now then, what is a consolidation process? Consolidation means put the things together in order with proper thought and thinking, so that it should have some functional values, so that it can be used. So it requires proper effort, proper time, energy, and at the same time proper thought and thinking and some idea and some innovation. Now let us see first the definition of consolidate. If you look at some of the dictionaries, you'll find these definitions like this. So that Oxford Language Dictionary, it gives the definition like this: combine a number of things into a single or more effective way, or you have to coherent the whole of the thing. So it says very simple definition, that combine a number of things in an effective way. Then what will happen? Then it will make the product or something more physically stronger and more solid. In addition to that, you can see these definitions also. Here you'll find that bring the parts which are separated into an unified way and unite and combine them, so that this will give a particular look, and it will be more stronger and more certain. Or not only in the product, even in the business also you can use this term, that is the consolidations. So putting so many things together for its effective use, that is the consolidation. Now, why do we require consolidation, and especially for product development? So that our product becomes more stronger, more structured, rigid and firm, and we can give a proper shape to that product, and the product becomes more solid, unified, and it can be effectively assembled together for its very effective functional value. So that is the idea of consolidation. Now, how to consolidate? How can we put the things together? First of all, it requires a number of components, and then we require a proper thought and thinking, and we have to give some effort, some energy, then we can put the things together. Now it just is a representation in this diagram. So these three blocks are put together with a proper orientation. Now if you want to put this also, then you have to give some effort and some time, and in a particular way only you can do it, so that it will get the final look. So who is going to consolidate? So basically it is the requirement of a teamwork. Teamwork means here, say there can be number of components. Those components can be manufactured in a different way, maybe in a same concern, or it can be from other concerns. And then we need to put together. So ultimately, that teaches us to become socialized also. So we have to learn how to move together, and so that we can develop a thing. So that is the requirement of a teamwork, that can be within the same concern, or even with the outer world also we can make it. So there can be one parent company, and that is producing something, and at the same time it takes the help of other subsidiary companies that are also called the ancillary industries. So if you want to develop a product, you are not developing yourself. At the same time, you are giving the opportunity for the development of others also, and you are all moving together. So that is another philosophy associated with the consolidation. So ultimately, you can move ahead with number of peoples together, and that requires really a nice effort, and that is a true example of a teamwork. Now, why do we require this consolidation? So if you look at any product, as I said, so here I have shown an example of the piston connecting rod, and you can say the crankshaft assembly that is used in the IC engine. So here you can see when it is assembled, these are like this. But when you take out the each and every component, you can see so many components are there, and those are put together in a particular order. And each and every component are to be manufactured accordingly with even different materials. So in that way, it becomes quite easier to manufacture and assemble them, because a complicated product is very difficult to manufacture. But at the same time, when we produce a small components or a simpler components individually, but at the same time, we should look into one fact, that the concept of interchangeability also, the concept of limit feet and all, so that we can put together. So it's not like that just isolation we can do something. So here you can see when we see each and every component requires its own importance while producing. And finally, we are putting them together. And at that way, the manufacturing becomes quite easier. And not only that, the manufacturing and design, the system design also becomes quite simple and what you call flexible. How is it that? Because say over the time, because the design and product development is an evolution process. Over the time you find that some new things has come up, or this piston needs a newer design. So that piston only you can design separately, then again you can manufacture in a newer way, and you can put it. So ultimately you are adding a flexibility to the system. Just think of if it is a single system, then just for making a single change, the entire product you need to scrap and new thing you have to produce. That it is not that very feasible. So in this way we can say that if we do the take the concept of say assembly or consolidation, the product design and manufacturing become quite simpler and flexible. Now, what are the products we do find in and around you? The product can be as simple as it is shown in this slide. So these are again assembled. Now you see this hobble. Here you can see one part and this can be the other part. And there are some pins also. So every product is important or every component is important to make. So you have everything, but you do not have the pin, then the product is incomplete. So here the importance to all, that is again one of the very basic concern. So this product, it is a consolidation product, or this box whatever you see, or even you can see a aeroplane, because these are a bit high end product mostly we say, and this is not a single piece, that is obvious, is not it? So how this kind of very what you call the sophisticated or very high-end products are being developed, are have been developed. So because we are putting the things together, that's why the things are happening like this. So if you see that the consolidated products with highly complex and precision components are manufactured for various sectors. It may be machineries, the automobile sector, or the aerospace sector. And here the many components, even subcomponents of these big products, that may be engine housing, gearboxes, or front frames, shrouds, panels, fairings, blades, vanes, anything you think of. So those you can produce, and then and phase by part, or in a hierarchical manner, we can put them together so that you can get the final product. So if you look at around, as I said in the beginning, there are so many components. So each and every, even this pen you can see, or that kind of turbine engine that you can see, or that cable systems you can see, or any metering devices, all are assembled together so that we can get the or we can find the importance of assembling the things or putting the things together. That is called the consolidation. Now, to do consolidation, what you require? We require a proper consolidation process, and that consists of the assembly of small components or single product uh, to put together so that we can achieve the desired geometry, the structure, or the property of this particular component. And for that, we require to apply some energy, and that energy can be a mechanical energy, can be in the form of chemical energy, or in the form of a thermal energy, so that the proper or effective consolidation can be carried out. So we need to interact, make the interaction between the material and the energy. Because without energy, you cannot do. Even you cannot simply move one component and put them together. Even you have a bolt and nut. For that also, you need to put them together. You require an energy. So without energy, it cannot be. So main thing is that the proper interaction between the material and the energy need to be carried out so that the purpose can be solved. But at the same time, when the material come across the energy, it may have some additional beneficial effect or some detrimental effect. Beneficially, I can say that the improving the microstructure during the forging. During forging, what do? We hit the material and we apply some forces in the desired direction so that the product takes its shape, and that is because of the permanent deformation of the material. But while doing so, we get one more advantage, that we get the proper microstructure, and the grains are oriented in a particular direction, so a fiber like structure we are getting during the forging. So that is the advantageous effect we are getting. But on the other hand, the detrimental or disadvantageous effect may also be there. Like when you are doing the fusion welding, you are apply the heat, and during the application of the heat, the purpose is to melt or the fuse the materials together so that they can be joined. But at the same time, the detrimental effect is your heat affected zone. Now the thing is that how to get rid of these detrimental effects. during the joining process, and especially the welding processes. Now, the consolidation, when we talk about the processes, then we have to employ this consolidation process throughout the manufacturing sequence. That is starting from the fabrication of the material or the production of that material. It can be in the powder form, or it can be in the form of billets, and that can be the solid material like bar, rod, wire, plate, sheets. All this, whatever we do, everywhere we need to consolidate, means the what amount of material in which way I should put together so that I can produce that particular material and in that particular form. And these are basically not the product which are being finally used by the consumer or the customer, but these are some intermediate products. So starting from producing the intermediate or product, or sometimes we say those are the raw materials, from that to the final product, everywhere in different phases you can find that the consolidation exists. Even you are producing the composites. Composites is again an example, because there you are having the reinforced material, and at the same time you have the matrix material, and these are made because of this polymer, graphite, metals, ceramic, so many different types. And after that we make some components out of that and we join, and there can be a different kind of joining process. So my topic is now moving towards the joining process, starting from the consolidation to the joining. And then I'll just make a small journey with all of you towards the joining process, and particularly we'll look into such a joining process where we'll find that what is the concept for having a less say disadvantageous effect, or we can say the more effective joining. How can we get it without having some detrimental effect on the workpiece material? So joining or welding and joining is a unique process by which you can consolidate the product. So it is also, you can say, is a consolidation process. And the performance of any component depends on how well the joint is made. So all of you know that the joining, the way the main base material is important, in the similar manner the joining is also. We have heard about the failure of many what you call many rather products, I can say big structures also, about the failure of the structure because of the weak joints, no? So the Titanic, that is again one of the example, that because of the failure of that some joints, no, the entire disaster took place. So here the joining is for what? Joining is for joints, or joints for joining the two components. So what is joining? Joining comprises a large number of processes used to assemble individual parts into large and more complex component or assembly. And those individual parts of a component meet at the joint. Now let us see, there are two examples of joining here. One can be a permanent joint and the joint can be a temporary joint. Permanent in the sense that once you put the or join all the components together, after that it is not easy to separate them. You have to make some breakage and then you can separate them. But in the temporary joint, those are quite easy to assemble and disassemble. So these are two different kind of joinings are there. And joinings are basically to take the load and pass it to. So that way the joining need to be quite stronger so that no failure take place. Now you see, the joining on the other hand can be divided in this way. It can be a kinematic joint or it can be a rigid joint. Kinematic joint, where do we see? In the mechanisms and the machines, so that a very constrained motion we can get amongst each of the components. On the other hand, the rigid joint, mostly we see them in the structures, because in the structure we do not want that the components should move with respect to each other. Rather, they must be much more rigid and stronger. So in our structures, in the buildings or some bridges, you can see the kind of joints we make, and there it gives a much more rigid structure. So the joining where you allow some movements, then it becomes a kinematic joint. On the other hand, when you restrict the movements, then it becomes a rigid joint. Now I am coming towards a rigid joint. So according to American Welding Society, the rigid joint can be of three types. That can be mechanical fastening, that can be welding, or is that can be adhesive welding. So all of you know that what is a mechanical fastening. Mostly we see the bolt and nuts. Those can be easily means opened and closed, or we can say we can separate them out very easily. On the other hand, welding is one kind of permanent joint, and you can see one example. The adhesive bonding, that is also a permanent kind of joint, and then it's not like that very frequently you can separate them out. So this is again one of the way by which we join the components together, mostly the ceramics which are not that very weldable. So in those cases we use some adhesives to join them together. Now I'm coming to the joining things, especially the permanent joints. So why do you want to join? So to restrict some degrees of freedom. So some degrees of freedom, if you are restricted, then it gives you a kinematic kind of joint, and that is mostly used in the mechanism. But a very complex shape you want to make it, then it is very much impossible or expensive to manufacture a very complex component. Then it is better to manufacture the components separately and put them together. And some products are better made as assemblies. And another advantage, that they can be dismantled at any time, even for maintenance. And on the other hand, the transportation is again a question. So you might have experienced sometime whenever we ask for some bigger or say a bit complicated product, then those products come to our side, and after that we assemble them together. So that is the advantage we are getting of joining the things together. Now, as I said that one of the rigid joining is the welding. So welding is basically a permanent join of two materials, and that is achieved because of the coalescence of material. So what is the coalescence? Because basically it is the merging of two or more particles into together, or we put them together, and that is depending on various parameters like temperature, pressure, and the metallurgical conditions. So if we put two particles together by applying some energy and maintaining some parameters like temperature and pressure, then those particles will unify, and that is again a coalescence process. And because of the coalescence, you can see the welding can be carried out. So that welding can be of different kind. That welding can be a fusion welding, it can be solid state welding, or even you can join the components by a heating process, and there the brazing and soldering. And these are all very much known to us. Now, if you look at the various kinds of welding processes, so you can see this figure, and you can see that so many different kinds of weldings are there. And some are very general. Mostly we see like oxyfuel gas welding, the arc welding and its different types, resistance welding, we are very much aware, and the solid state weldings are also there. But at the same time, there are some unique processes are like the thermite welding, laser beam welding, electroslag welding, flash welding, induction welding, and electron beam welding. So why do we require so many? And especially this kind of very unique welding processes are also very much helpful in some particular applications. And what is their uniqueness? That again we are going to see in the subsequent slides. Now, whenever we talk about the joining, so mostly it is the interaction between, especially welding joint, I mean here. So it is a interaction between the two parent material. Those are say the two plates A and B, we are joining them together. But at the same time, we put sometime a baking plate or metal, that is the C, and we can have a filler material also, the D. So ultimately the weld pool, whatever we are getting, it is a basically it is a complex alloy of these four different materials, that is A, B, C, D. A, B, the parent, the plates A and B may be similar material, may be dissimilar material, and the baking material and as well as the filler material. So ultimately we get a joint. Now, how big should be the whirlpool, how deep it should be, how nice it should be, how strong it should be, or at the same time, when doing the process, so what happens to the nearby material? That also is a matter of concern. So now you look at this drawing. Here you can see this is the whirlpool or the weld metal, and near, so it is, as I said, is the consolidated molten material, and which is here to join these two pieces. But on the other hand, you can see the nearby material, those are also getting affected by the heat whatever is being applied, and that is called the heat affected zone. And why this heat affected zone? Because when you hit the material and the temperature reaches quite high, and that temperature might be the transformation temperature or the recrystallization temperature, then this material and changes its structure. So if the material changes its structure, that is not the desired material, which exactly we wanted to join. And here you can find there may be some detrimental effect. The material becomes very brittle. Some cracks may be initiated there. So ultimately, there is a chance of failure of the material in this zone even. So then how can we reduce the effect of heat in the nearby material? So then what kind of sources I should use so that the effect of heat uh, on the workpiece can be minimized or can be avoided? So if you look at this diagram, you will find that this is a photographic view of the microstructure of a welded joint. It can be a multi-pass or two-pass material. So weld metal, this is weld metal, these are the base metal, both the side, and you can see it is the heat affected zone in and around. So this heat affected zone makes the joint sometimes weaker. There can be a weld zones with a single pass, there can be multiple pass. And you can see here the nearby area, it is being affected. So this is just a microstructure of a welded zone. Now, then what is this heat affected zone? This is basically adjacent to the fusion zone area. It is within the base material, and that is very much undesirable because it is a heat affected zone. And this adjacent metal will experience sufficient heat to bring about the structure and property changes. And that is because of the phase transformation, recrystallization, grain growth, precipitation, or precipitate coarsening, embrittlement, or cracking. So that so many things may happen. And because of that, we are getting a different material than the parent material. And most of the failure occurs in the heat affected zone, and that is the most weakest area. That is the most weakest area. Now, we are going to look at how this can be minimized. Now, if you look at the deliberation of heat energy to the workpiece material, it can be in a two different way. One can be a low rate of heat, means you are giving smaller amount of or lesser intensity of the of heat, and very slowly you are applying the heat to the product, and ultimately that heat, before going to make any changes in the material, it may again get dissipated inside the material in a very unwanted way. So ultimately, we are getting large total heat content because the heat is getting dissipated. And just to melt that material, we need to reach that temperature so that you can melt the material so that the material may get fused together. So we need to raise the temperature. But as you are applying at the heat at a very slower rate, what happens? The heat get dissipated so that we require more and more amount of heat, and ultimately the heat is being gained in a larger area, and that very slowly the heat is raising the temperature, and it is and at the same time the material is getting cooled also, and that also takes a larger time. So that means the cycle time of giving the heating is too large. and then we are getting the large heat affected zone, and ultimately that lowers the strength and hardness of the structure, and it increases the ductility also. So this is one effect. On the other hand, if we apply high rate of heat input, then what happens? So then we require lesser amount of heat. So ultimately purpose is what? Purpose is not to just to pump the heat inside the material. Our purpose is to make the required changes in the material. And what kind of change we want? We want that only the portion where we want to make the joint, only that portion should get melted, and it should get fused together with the other its counterpart. And then the heat need to means taken away from the system, so that the system remains cool. So we want faster heating and faster cooling. And if it is so, then the energy will not get its chance to get dissipated inside the material or the nearby material. And if the heat doesn't go inside, then it's quite obvious that we are going to get the smaller heat affected zone. That is again one of the important issue. So now you see one example of a weld joint, and this is because of the high energy rate high energy rate at beam welding. So here you can see the width by it's a dip ratio. If you see, so it is much more deeper than wider. So in that way, what you are doing, even a thicker plate, uh, you can join up to the depth very effectively. But on the other hand, the weld joint is not very well spreaded, and we do not want that. So we want that only very localized heating, so that only at that area you can make the changes, and rest of the material should not get affected much. Even by a single pass you can and reach quite deeper, and you can uh, get the material welded, and without applying very less amount of energy. And if you apply lesser energy, it's quite obvious that the heat energy will get dissipated lesser, and you will get the smaller heat affected zone. Now, to do so, then what kind of energy sources we require? That is the main concern. It's not like that in any welding process, say like the gas welding, or you are welding the arc welding, and we are trying to achieve those conditions that quite I want to reach quite deeper, and so that no heat affected zone. It may not be possible. Then you require a proper source of energy, and with that intensity, so that you can carry out those changes in that very manner as you require. And that is the very restricted area you want to heat. Now you see a comparison, a very nice diagram. It talks about that what kind of source of energy you are using, so that the wide spread of the whirlpool and the heat affected zone can be restricted. Now you see the TIG welding. In that case, the yellow mark. So you can say your width of the weld is much bigger in comparison to other. Then MIG, a bit lesser. Plasma, restricted. Then laser, you can see the purple color. So it is quite lesser than the other. But if you look at the electron beam welding, it is very much restricted. So if you do the welding by laser and the electron beam, you'll find that the heat is not being dissipated too much in the nearby area, because of the nature of the way you are applying the energy. It is because of the shorter pulses and high intensity, so that it remains within the confined area, but it can reach up to the depth. So ultimately you can say the penetration is more than the dissipation in the nearby area. So you want high penetration, and in a very shorter duration, the entire process need to be over, and the nearby area should not get affected. So that is the philosophy that you should use it, so that you can get a very effective welding and clean welding. Now, just that philosophy I wanted to explain it here. Now, say this is applicable not in welding, even we are using some non-traditional machining processes also. So we say them as an electrothermal process because we are carrying out the change in the material by applying some amount of heat. So those processes are called the electrothermal process. Why it is thermal? Because we are using thermal process, and mostly we take the direct source of electricity and convert them by some means so that we can process the material. That processes can be any manufacturing process like welding, cladding, or even the heat treatment. And on the other hand, it can be removal of the material. That is nothing but the machining process, and with the application of the heat. So in that case, we want to heat the material at the desired location of the workpiece to melt or it vaporize it. Now, if you want to do so, then we require a different and particular sources of energy that can be spark, laser, electron beam, or plasma, and which can be produced directly through the electricity. So just by burning the coal or heating the material inside a oil bath or water bath is not enough. We need to find a particular source of energy which can raise the intensity up to that level so that the desired change we can make it only in the localized way by the nearby area should not get affected. Now look at this diagram here. Look at this diagram here. You'll find that in this particular workpiece material, this is the point of interest. This is the point of interest where you want to apply the energy, and this is the point B where you do not want to make any changes, and you want to have the energy confined within a particular zone that is called as this is the control volume. In this control volume you wanted to apply the energy so that whatever the changes you want, what change basically, you need to melt the material, or if you want to vaporize the material if it is a machining process, but the nearby area should not get affected so that the heat energy should not get dissipated in the nearby area. So that's condition we need to achieve. So the heat energy should not get conducted or dissipated. So you have to again win over the conductivity of the material. Now, if you draw this temperature versus time line, you'll find this is the way you can raise the temperature over the time with the particular source. Now, this line can be drawn for some other source like this. Some source it can be more vertical slant, or some source it can be more steeper. Now, it depends on what kind of sources you are using. If you are interested in the much steeper, that means within a very small time you are raising the temperature quite fast. So you need a particular kind of source. But on the other hand, say you a very say slant curve you are opting for, then you can see to reach the temperature you require a very long time. Now, this time is a factor. So, in a what short duration you are making the change so that the energy will not get any time to get dissipated. So, that is the thing. Now, for that, what kind of the sources of energy it is required? So, in traditional processes, we mostly we apply the heat which consumes a very high heat just for bulk heating, because whenever we apply the heat, before that it makes the changes in the material, it hits the nearby area also. So you require very high amount of material, and that is being wasted just for bulk heating. High level of thermal distortion you are getting, and if it is so, the product whatever you are getting, that is quite inaccurate, and at the same time some undesirable changes, structural changes you will see on the material. Those are nothing but the alteration of the material, that is the heat affected zone. And if you get this kind of detrimental effects, it's quite obvious that the surface life of the material or the product is going to be affected, and it will be not that reliable. And these things are happening because you are giving a continuous heat source on the workplace material. So what to do then? Now you just look into this diagram once again. Say point A and nearby point B. And you are giving three different sources. One is the short pulse, long pulse, and very long pulse. Pulse means the duration in which you are applying the energy. That is one duration of the pulse. And in a pulsating mode also, you can give the energy. It is not necessary that always you should or the pump the energy in the continuous mode. So in a short duration, you are applying. So if it is a shorter pulse, then you see what happens. So there are two curves you can see in this particular diagram. One is for A, another is for B. So you see for A, the temperature rises like this. By this time, the temperature rises to the vapor point at point A. What happens to B? You see, the B is quite apart. And by this time, A is at vapor point, B is here. And B is not only below the vapor point and melting point, but it is well below the T star. This T star is nothing but this transformation temperature or the recrystallization temperature. And if you achieve this condition, then you can see that whatever the changes you want to carry out at A, it will be there. It will get vaporized. So you during the machining, you want that the material should get melted and vaporized. We can remove it. But at B, even it is below recrystallization temperature. So we are expecting that no much damage will take place in the material at B. So it is very ideal for perfect machining. And even you are welding, then you need not have to achieve there. You can go up to this. Just move above the melting point, and then you see what happens at B. It is below. So in that way also you can go for very precise welding. And if you are using a bit long pulse, then you see by this time you are reaching your point A is reaching at at A here, and sorry, I have the A here. You see B is here. That means A is getting vaporized, but B is again above melting. So ultimately, even though you are machining there, it is because of it is having some high thermal distortion, because the nearby material B is also get melted. So that is not good. Now, on the other hand, you see, you want to achieve it here, the very long pulse, A is melted and nearby area B is also melted. Now, as you know that machining area and welding area are different. In machining, in a particular place, just we want to remove the material. But in case of melting our contour volume, it is a bit larger. So if by chance say B is within that range, then you can say the B, A and B are welding, but there can be a C point, that the C point it is here. So if it is below that, say here, then you can say that it will not get changed. So now from this diagram, what you have understood, that what are the desirable point, whether A, B or any point nearby area C, up to where you want to heat, and what happens in the nearby area, that you can control by applying the energy in different pulses, and by controlling the duration of the pulse you can restrict the effect. So here in high energy rate electrothermal processes, you need to achieve these two conditions. One is high energy density. Apply the energy per unit area, that is high. Energy requirement is not high. Energy per unit area is high. That is the energy density, or the energy per unit volume. That also you can calculate it by this kind of equations. And on the other hand, you have to see the shorter pulses. How fast you are applying that energy to the material, so that the nearby area will not get affected. Because who will hit the nearby area? The conductivity. So the conductivity will not get the chance to take the heat. Before that, you have completed the cycle. that you have melted the material and we have withdrawn it, the energy source for that duration, and you have cooled down. And then again you use the next cycle of heat energy, so that again you can carry out the changes in the next area, so where you wanted to carry out the machining or welding, whatever. So in this way, you can see the same amount of energy if you want to apply. So the power density and time, if this amount of energy, that is the by the area. So it can be in a very ultra short pulse, medium pulse, and the long pulse. If you want to carry out a very surfacing operation, then glazing, cutting operation, the short pulse, then welding operation, the medium pulse, and very long pulse you are giving for heat treatment. Because heat treatment, the area is a bit more if you want to carry out, and that intensity is not required. But in welding, the area is restricted, but not that much of that of the heat treatment area. So here a bit longer pulses or the medium pulses can be helpful. But if you are doing the machining and cutting, in that case the much more shorter pulses. So what we have understood, that we have to select such a source of energy in which we'll find a very high energy density. At the same time, in a very shorter duration we can apply it, so that the nearby area will not get affected. And that's why in welding you can see that low rate of heat input welding, moderate rate of heat input welding, and high rate of heat input. And in high rate of heat input, you can see the plasma arc welding, electron beam, laser beam, and the percussion welding on the spot and seam resistant welding. So in this kind of welding processes, you'll find that the effects are lesser and quite deeper welding we can get it in comparison to this kind of welding. Now, if we compare the energy density for different kind of welding, gas flame welding, you can see 10 watt per centimeter square. TIG, we are getting 150 watt per centimeter square, whereas electron beam and laser beam, you can see 10 to the power 7 watt per centimeter square. And that's why you can see the seam of laser beam welding or the electron beam welding, though are so clean, so fine, and so deeper, and so that you are getting a very nice joining. You can get a very nice joining there. Now you just see the comparison of this 10 to the power 7 and only 10. So so the gas welding, and you can see the difference between the laser and beam or the electron beam. The main change is there with this, your energy density. So this amount of, or the power density, whatever you can say. Now you can see the heat input and transverse sinkage for welding material. So how much the material is getting sink. So the material thickness is 12 millimeter, and by different materials we are welding, then you can say the shrinkage is minimum here if you are using electron beam welding, because of its high energy density or the power density. Now the electron beam welding I am coming to there, and how it is to be performed. So of course the time is running out. So it is very much ideal process, so that you can get a very clean and efficient joining there. And we know the mechanism of how the electron beam is generated. It is generated inside the vacuum chamber, and it can be controlled by the focusing and deflection coil, and it can be placed on the workpiece material, and its power density is this much. And these electrons are strike on a workpiece, so that the kinetic energy of those electrons converted into the thermal energy, and then we get that very high speed, so high intensity of heat, so that the required changes we can do. The same electron beam, just by controlling the power input, we can use for machining, you can use even for the welding also. Now, this is the concept of keyhole welding. Because of that high intensity, you can see the material when the beam is falling there, suddenly it vaporizes and a small hole is created, and the beam enters a bit more and then you can see a keyhole kind of thing it is formed, and nearby a material is getting melted. And as you feed the material or travel this give this means make the travel of the beam, you can see the trailing area is getting solidified like that, and quite deeper welding you can get it. And this concept is called as the keyhole welding principle. And this electron beam welding has got one restriction, that it need to be performed in a vacuum, because the electron can easily flow inside the vacuum. But if it is in the air, then it cannot move forward, because the electrons are the very tiny particle, and when it come across the heavy molecules, it cannot move freely. So we give that vacuum environment, and this is the order of vacuum it is required to generate the beam and to propagate. But this requires a very long hour pump down time, because you have to create and you have to create the vacuum, and again you have to then devacuum on the system. That's why it makes a slower one. So that can be another one, the medium vacuum welding, and there can be no vacuum welding. So if this kind of weldings you see, but if you see the no vacuum welding, there is a lesser penetration in comparison to the high vacuum welding, and the medium vacuum welding is just the moderate amount in between these two. So this is again another effect of the vacuum. So if you are having high vacuum, you can see the penetration. And on the other hand, when this electron, this the beam, the electron beam propagation, you can see it is flared. So ultimately, this area is not that controlled. So it depends on how do you use the vacuum, or how do you propagate that beam to the workpiece, and accordingly the desired effect you can get it on the workpiece. At the same time, in air, if you are doing no vacuum, with the air you are doing, or even just you are not allowing the air, but you can blow some helium gas, lighter one, so that some a higher aspect ratio you can achieve. And it is so fine that sometimes the area cannot be covered. Then you need to cover the area by moving the beam like this, or just like this, so that a bit wider if you want to machine, that can be possible, just this, but deflecting the beam so that it can cover that larger area if you wish. And these are some of the parameters of welding, electron beam welding. I'm not going to discuss this right now. And these are the comparison. One biggest advantage you are getting, that even by a single pulse, quite a larger thickness you can weld it. Whereas in other process you see so much of the, so whereas 180, 60, 60, 200 number of passes are required, and there only one pass can machine up to say up to machine, it can say weld up to 300 millimeter deeper plate also in one go it can do. So you can see the number of passes in electron beam. That is the depth it can achieve. There's only one, because of the high density and area low. So it is quite focused. It is quite focused. So nice welding you can get it, and the heat affected zone will be minimum. These are the advantages of electron beam welding: low thermal input, high aspect ratio, high purity, deep penetration, and it welds very high conductive materials also. That is again another, because you have to win over the conductivity. We have to win over by this time the conductivity dissipates it, before that you just complete the cycle. So that fast it should be, and that's why we require the shorter pulses. The disadvantage, the high joint preparation time and cost, the non-productive pump down time, limited penetration if the stand-up distance is high, or even no vacuum. Then another is the X-ray shielding is required, because of this interaction of electron beam over the workpiece material. Some X-rays may come, so it requires the proper protection. And seam tracking sometimes difficult, because it is inside the vacuum chamber. Then the conclusion of today's discussion. Mostly we'll see the products are consolidated in nature. And consolidation makes the product development quite simple. so that we can design and produce the components in a very what you call discrete manner, one by one, and then we can put them together so that a very complex product can be fabricated. We require some energy that can be mechanical, chemical, or thermal energy, and that need to be applied very effectively so that the proper bonding between the material take place. At the same time, we should not get the detrimental effect of that energy on the workpiece material. And welding is one of the very important what you call this joining process. And if I want to choose uh, a very big spectrum of the energy sources, you will find that the high energy rate heating will have the minimum heat input and minimum heat affected zone, and that require these two conditions: high energy density and shorter pulses. So accordingly, the source I need to find it out, which can give me the high energy density and shorter pulses, and that's why we are going for laser welding or electron beam welding. So electron beam welding is one of the ideal process for very precise, clean, and weld with minimum heat affected zone. And EBM is one of the excellent. So one side we are having simply a gas welding or arc welding. On the other side, we are having the electron beam welding. Now it is up to you. In between, there are many more. What exactly you want and what effect you want to make on the workpiece, what changes you want to make on the workpiece. So accordingly, the required process need to be selected. I do not say that always we should be on the higher side, because looking at the requirement, we have to go the other side also. So this is about the entire discussion today, and these are the references I have consulted in preparing these slides, and my entire discussion based on these references. And thank you. And this is the guest house at NIT Silchar. So I also welcome all of you at NIT Silchar. Whenever you get any chance, any occasion, please do visit us at NIT Silchar. Thank you.
Thank you so much, sir. Thank you, sir, for your wonderful lecture. Now this is the time for question answer session. Audience, if you have any query, please raise your hand, or you can write it in chat box also. Let me check if anyone has any query. Audience.
If you have any question, please, or you can contact me over phone or sometime even over email also, if you wish, sometime, if you want to talk to me, so that we can interact even later also.
Okay, thank you, sir. Sir, there is a question, I think. Mithun Mandal.
Hello, sir.
Yes.
Hello, sir.
Yes.
Sir,
Yes, Mithun Mandal. Please.
can I speak? Sir, can I speak Bengali?
Yes, I can speak Bengali if you
Sir,
wish. Even but other people may not understand. I do not know. But okay, you can use. I'll try my best to give the answer.
ওকে স্যার। স্যার আপনি বললেন স্যার ওই যে মেটেরিয়ালটা মানে গামার কিংবা এই এর মাধ্যমে ইউজ করলে স্যার বোরিং কি স্যার করা যাবে? মানে মাটি কি খুঁড়ে মানে মাটি কি খোঁড়ার মাধ্যমে মানে আমরা কি মানে পৃথিবীর লেয়ারে মানে একদম শেষ লেয়ার টাকা যেতে পারবো গামারের মাধ্যমে? হাই পাওয়ার যদি করা হয়
Gum.
কোনো, যদি স্যার হাই
Now
পাওয়ার
here
ইউজ
the
করা
thing
হয়।
is, yes, yes. Now here I have said one thing, that we do not require much amount of material, but the intensity. It's okay. But at the same time, the amount is also important. It's not that. Now the thing is that whenever you are doing welding or boring or machining anything, then whenever mostly I am focusing on the smaller or micro machining or micro manufacturing or micro welding level. So there our requirement is very minimal, so that with that very high intensity we are applying the energy, and the quantum of energy that we are applying, that should be sufficient to make the changes in the material. I said I have shown one equation. There you might have seen that I need to move up to the vapor point. For that, what amount of energy it is required? Now the question you are asking, that I want to bore the earth. Now what volume of material you have to remove, so that you can dig a hole in the earth, and for that what amount of energy it is required? Can you deliver that energy with that intensity? That is the question. So I don't think that it is that very feasible, that amount of high intense energy we can apply and we can take out this. And not only that, even though you are applying that energy for digging a big hole in the earth, then even at some layer you can make the changes up to some level. But at the same time, the material which you want to remove it, you must have a mechanism to expel the material and flush out the material. That is again one of the biggest challenge. So two challenges you have to overcome, that very high intense energy of that quantum amount, that quantity you need to apply, and at the same time how to take out the removable material. So that is the issue related to that very high volume of material. But usually we do not apply this kind of sources just to dig a hole on earth. So for that, how the ONGC or oil people, they are doing and they are doing the boring and extracting the oil. But again, you are talking about one more thing, ki পৃথিবীর মানে সেন্টারে যেতে পারি কিনা, ভাই অতটা knowledge আমারও নাই. Thank you.
Okay, sir. Thank you, sir.
Yeah.
So I think Maul Hawk, he has also a question. He has raised
Yes,
his,
sir. Sir,
yes.
Yes.
let's because EDM and those machines are advanced. So, what are the main thoughts how to maintain those machines? Like, if someone wants to use for a long term and use those
Any
so-
machine. It's not like EDM, EVN, laser, whatever. Any machine, whatever you procure, which is at your disposal, you must take care. That is the first mantra. And you should feel like that machine is your child, that machine is your brother, that machine is your one of the family member. Many a time we see that the people are just entering the lab with an intention that I must get my work done, and after that whatever is done, means whatever is left, it is not my concern. That should not be. First of all, we should respect our machine like the aspect we ask for ourselves, because your machine may not be having that feeling, but it can show you its feeling. Because one day you are doing in a very harsh way, you are not working properly, just as a selfish person you have done your work. Just think of this. Next day whenever you will be going, definitely the machine will show its own anger to you, because it will not work, and on the next day definitely you will have a problem. So my one thing I want to propagate, that whatever the machine, maybe it is an advanced machine or even a simple, say, saw cutting machine, if you are having, every machine has got its own way to maintain it, own way of maintenance. So please do enter the lab, see the manual, try to understand the requirement of the machine. Now especially I talk about, say, electrochemical machining process. In electrochemical machining, what happens, we are using the electrolytes, and we know the electrolytes are quite corrosive in nature, and you are working on that machine, and because of that machining process, you have, say, not taken care properly, and you have, say, put your workpiece there for a very longer time, and the different components are coming in contact with that corrosive atmosphere, because the electrolytes are quite corrosive mostly. Then whatever the care initially you have taken to prepare your work pieces and all, and later on you are not taking care of that, you'll find that there will be so much of oxide layer and all on your workpiece, and that result you cannot publish in a very decent way, is not it? So not only the workpiece, not only your workpieces or the tool, the entire machine, that nearby area you should take care. And every machine requires its own maintenance. And one more thing, the schedule maintenance, the proper, those things also you should keep in mind. That's all. It's a very general way, I can say.
Okay, thank you, sir. I think Maul, you have got your answer.
Yes,
Now,
thank you so much, sir.
okay. So
Maul, thank you.
we have one more question from Niranjan Pal.
Yes,
Thank
please.
you very much, sir. Sir, thank you very much, sir. First of all, sir, I have a small questions. Question regarding the uh, welding or bonding, adhesive bonding or riveting. That means bolting. Sir, I simple question is that when two materials are welding together, at that particular person, sir, the strength of material should be slight should be decreased or it's same, sir. Because of due to welding, it may be change
Your
its
voice is interrupting. Your voice is interrupting.
okay, sir.
Can you repeat the later part?
Okay, sir. Sir, when the welding with two materials, any kinds of material, two materials of welding, at that particular person, sir, the strength of material should change or it should be same, sir, after welding.
Change means there are two change. One is increase, another decrease.
Yes, sir.
Is not it? So what do you want?
Yes, sir. Yes, sir.
Obviously, you do not want that decrease in the strength. You want let it be same, or it should not decrease, rather increase. So whenever we make a weld pull, basically it is an interaction of your material that you are welding as well as your filler material. And if the gap is too high and you have prepared the edges of the plate and the gap is too high, sometimes that autogenous welding may not serve the purpose. That means you need to put the filler. Now you have to choose the right filler so that the right strength you can get it. So my concern is the strength should increase rather decrease. So you should use the right filler so that you get the required strength on the material.
Okay, sir. Thank you very much, sir. Yes, sir.
Yes.
Thank you very much, sir.
Thank you. Thank you.
Okay, I think no more questions is there. Thank you, sir. Now I would like to present a small token of appreciation for the respected keynote speaker, Professor Dr. Pramod Kumar Patwari, sir.
So thank you.
Thank you. I'd like to request Gautam, sir, please. Yes. Sir, please accept it. This will be mailed to you by our organizing committee also shortly. Thank you, sir. Please accept it.
So once again, thank you for this appreciation. And I am thankful to the entire fraternity of this Allied College of Engineering and its administration, its faculty members, its students, and the staff all. So that I could be present virtually with all of you, and I could deliver a lecture with you, and for giving me this opportunity. Thank you. Thanks a lot.
Thank you, sir. We are fortunate enough to have you among us in this national conference. Thank you, sir.
Okay. Thank you. Can I leave now?
Yes, sir, you can. You may. Thank you, sir.
So thank you all. Thank you for your patient hearing, all the participants.
So moving to the next segment of the session, contributory presentations on mechanical engineering. As already mentioned earlier, Dr. B.G. Gupta sir is the session chair, and our honorable judges are Dr. Shubhashish Banerjee and Dr. Ashwini Kumar Sharma. They are already present among us. So there are four contributory presentations in this session. Best paper will be awarded at the end of this session. Maximum allowable time for each presentation is 10 minutes. So contributory presenters are hereby requested to kindly finish within due time. And once again, I would like to request the audience to raise your queries at the end of each session, or you can write it in chat box also. The paper one is a student paper and it is on multipurpose wheelchair, authored by Vishwarup Poddar. I'd like to call upon Vishwarup Poddar to start his presentation. Over to you, Vishwarup. I think you are present now.
Yes,
Yeah, you can start.
okay, ma'am. Thank you so much.
Okay.
Good afternoon, everyone. I'm Vishwarup Poddar, and I'm the ex-student of Elite College of Engineer. And nowadays, I'm working as an AI researcher in GlobeSync. Especially thanking Elite College for giving me this opportunity to build my dream project. And I love to thank our principal, Dr. S. Bashak, and our HOD, Dr. Krishna Hazare, and Moha ma'am and Abhijit sir and other faculty members to supporting me this position. Now I present my PPT. You can find there the multiple wheelchair. Okay, everyone know that there is many types of wheelchair in our country and in our world also. But these types of wheelchair are not able to climb the stairs and rough surface. So I built this project for medical health and our disabled people who can easily travel and move. This is the diagram how the stair will be can climb. Okay, this is the stair and this is the wheel variant. How the stair will be climbed. Some history about the wheelchair. We know that wheelchair is not today's model or today's based on the manufacturer. So this is the Asian period in the China where the first wheelchair came, and some people will hold the wheelchair and move forward. A single person cannot move. They need one sitting and one people, which one will be praised. The types of wheelchair. This is a normal wheelchair based on nothing. This is a simpler price like 5,000 to 17,000 approx. It is a simple based wheelchair in our market. And nowadays we can find the stair lift wheelchair which can easily climb in stair, and it is very costly in our market. And the third one is a multi-purpose wheelchair. Yeah, it is also too much costly, around 6 lakh, 9 lakh, 20 lakh also, and it doesn't support every features. So that, and some other models like smart wheelchair in a commando section and some road basic model, and sports wheelchair related to sports like football, racing, and other things also. This is the literature related to the wheelchair, how I made, and the new wheelchair climbing base designing and optimized designing, how it is work like a machining, like a first start with the designing. Designing is the main fact where the wheelchair is came. Because the when I think the how we climb my wheelchair in the stair and a rough surface, the first idea came about the designing. After I complete my designing, I came into the manufacturing thing. Which types of material should I use, and which is costly for outer market and also for me, and how easily it will be movable for each and every surface, and the basic concept of the circuit design, because it is not a totally mechanical project, it's also part of a electrical, some basic techniques also. That's why. And after I completing the project, how the other people can figure out in the market and the shop also. This is the prototype. This is the basic prototype which I make and run in a AutoCAD and a CAD CAM position to signify. This is the prototype model which I make at our college, and this is the formula which I use to make this thing. In my building prototype, after completing the whole project, I can travel it with a 70 kg in a 2 kilometer distance, and with a 100 kg with 1.5 kilometer distance. This is the test video. You can watch here. This is easily can travel from topper end to bottom end, but in the bottom end to topper end is not easy to climb, but it can easily climb by its heavy wheels and heavy power also. The design will make these types, it can also climb the stairs and downwards to the stairs also. In a single way, it can rotate 360 degree. Okay, this is much. Thank you so much. Thank you, ma'am.
Yeah, Biswaru,
Yes, sir.
you have taken this, you have actually created the prototype, right?
Yes, sir.
Okay. And this prototype works with how much payload?
This prototype only carry that 70 to 100 kilometer, 100 kg.
No, I'm talking
always.
about the prototype you shown.
Oh, the prototype, sir, only 10 kg.
Can this take 10 kg?
Yes, sir. Because I used with a brick.
I did not get it.
Hello, sir.
Hello.
Yeah.
Yeah. What was the weight of this prototype, what you have shown?
The weight of the prototype is too much low, because this is made of the PVC pipe and other plastic compulsory things. But after
Okay.
I'm making this prototype into a metal, with the metal pieces, it can carry much better and much
What you
heavier.
are doing right now? what you are doing right now? Means, are you doing your BTech or you are done with
No,
BTech?
no, no, no. I'm pass out BTech, and right now I'm doing my job. Actually, I'm a AI researcher.
Okay, fine. Right. So basically, you need to work on the design part of it.
Yes, sir.
Most of the time, simulation of it,
Yes, sir.
and after that, maybe it will work out. Okay.
Yes, sir. Yes, sir. Sure. Thank you.
Okay. Dr. Is Banerjee, sir, do you have any question to the computer presenter?
Yes, Vishwa, I have a question.
Yes, sir. Please, sir.
Actually, normally wheelchairs are for physically handicapped people, normally what we
Yes, sir.
understand. Okay. So this is, there has to be an operator who has to run the wheelchair,
Yes, sir.
right?
Yes,
But
sir.
in your prototype, you have shown this is not manpower, this is the remote
Yes,
control,
sir.
something like that. Okay.
Yes, sir.
So my question is that the person who is boarding on the wheelchair, he or she himself can operate the wheelchair, right?
Yes, sir. With a joystick, with a very significant and small joystick, which is fixed on the wheelchair hand, it is
Mhm.
operating very suitably.
Right.
Yes.
The prototype which you have shown, you were
Yes.
telling it can carry maximum up to 10 kgs, right?
Yes, sir. Yes, sir.
So if you want to operate this sort of wheelchair where you do not require any operator, if person that physically handicapped person, he himself or she himself can operate it. So human body weight plus weight of the wheelchair. What should be the weight of the wheelchair which you are thinking of?
Uh, Sir, if the human body weight is 70 kg,
Mhm.
then the total amount of the whole thing is around 90 kg, because the wheelchair need 20 kg, because they carry the battery and the other features also.
So okay,
That's
tier
why.
weight of the wheelchair is around 20 kgs,
20
right?
kg. Yes, sir.
And plus the weight of the person who is boarding the wheelchair.
Yes, sir.
So roughly something less than 100 kgs, right?
Yes, sir.
So with that load, can it go uphill? I mean, with the stairs, not through the ramp.
No, sir. It can carry with the person in a stairs, because the gyroscopic matter also inbuilt in there.
Mm.
That's why the weight is totally based on the surface, the downer surface of the body of the wheelchair, which can elaborate the significant space also. That's why, sir.
Suppose I am a physically handicapped person, I cannot walk, that's why I am using a wheelchair, right?
Yes, sir. Yes, sir.
And this sort of wheelchair, I do not require any operator. I myself can operate the wheelchair.
Yes, sir.
So this is a sort of, have you seen forklift trucks for
Yes, sir.
material handling?
Yes, sir. Yes.
Hmm?
Yes, sir.
So this is a sort of that version, but material handling equipment cannot be run through stairs.
Yes, sir.
Your wheels are designed like that, as you have shown in your presentation, that
Yes,
it
sir.
can go upstairs also through that stairs, not through the ramp.
Yes, sir.
Hmm?
Because the stairs are very much difficult to climb or to came downward.
It is very
That's why
difficult to climb. At the same time, you have a different gradient also. In the
yes, sir.
different house, you have a different gradient, different yeah, also that, what should I say, the gap between the
Yeah,
each of the
yes, sir.
stairs,
The
that
angle,
also varies.
Yes,
So it cannot be standardized like that, I think so. Can it be?
sir, I designed with the angle because I can find that it can be movable.
No, it
That's
can
what.
be movable. That is not a problem. If you move on a plane surface, it can move. If you move on a ramp, it can move. But it is difficult to climb the stairs, isn't it?
No, sir, it can climb the stairs, because in my prototype there is not too much power. That's why it takes a little bit problem. But if I give them a bigger version, I will build the more power. It can definitely climb the stairs also.
Yeah, but again, you have to take care of the design of the stairs, na? If it
So
is
it is
little bit
totally
wide, then again it will get stuck.
no, sir.
Anyway,
The wheel
yes.
was rotating like a 360 degree.
No.
That's why.
Wheel is rotating 360 degrees. That is on the
And
plane surface. You can move, or you can change your direction. But while you are
but
going upstairs, that time if the width of the stairs are more, in that case your wheels cannot work everywhere.
sir, it can climb also. I can show you the picture.
It
Give
can
me some.
climb, but again it depends on the width of the staircase.
Sir, it's a
Isn't it?
basic thing, sir. It's a this is the prototype model.
Hmm.
You can show. Let us say. Sir, this is the angle formation which I made, and the angle formation is a climber. With this climber, it can move. The
Oh, it can change.
yes, sir. It can change
Okay.
this angle
Okay.
when it move forward and climb the stairs. Then
Mhm.
it can change.
So that amount of flexibility is there.
Yes, sir. That's why.
Okay. Okay. That's what I wanted to ask.
Yes,
Okay.
sir.
Thank you.
Thank you, sir.
Thank you, audience. If anyone else you have any query, please you can ask. Otherwise, I will move to the next paper. So thank you, Vishnu, for your wonderful presentation and the prototype model. So now moving to the second paper, the
Thank you,
topic
ma'am.
of second. Thank you. The topic of second paper is influence of thermal boundary conditions on natural convection heat transfer in a wavy walled square cavity with adiabatic block. Authored by Dr. Shantanu Datta. I would like to request Dr. Shantanu Datta to kindly start his presentation. Over to you, sir. Thank you. Hello, sir. Uh, Sir, it is not in full screen mode.
Dr. Shantanu Datta, you are not audible.
But sir is unmute, I think. Sir, hello.
Am I audible right now?
Yes, sir, you are now audible.
Okay, so let me present my paper. This is
Actually, you are not in full screen mode. So
Yes.
if you have any problem in full screen mode, better we can play from our end.
okay, sir. Then you can do it, sir. No problem. Then I will stop sharing.
Okay, sir. I would like to request our web host, Professor Gautam, sir, to kindly share his PPT.
Okay. So it is perfectly all right. So
Yes, sir.
thank you so much for the organizing committee, the moderators, and the web host for taking the time and patience for presenting the paper. I will tell on behalf of the someone who is presenting the paper. Okay. So first of all, I want to thank the organizing committee for selecting my paper. So the paper title is Influence of Thermal Boundary Conditions on Natural Convection Heat Transfer in a Wavy Walled Square Cavity with Adiabatic Law. Next slide, please. Okay, so the table of contents is introduction, motivation and objectives, results and discussions, conclusions and scope of future endeavor. Next slide. Okay, so here in this particular slide, I will tell something about the uh, overview of the natural convection. So this was my PhD topic when I did my PhD from National Institute of Technology in Durgapur. So natural convection is a mechanism of heat transportation in which the fluid motion is not generated by an external source. Okay, and some studies displaying natural convection in enclosure are given below with different situations in real life, which are very important for day-to-day understanding. So first of all, natural convection in an enclosure with porous media. Okay, so this porous media heat transfer relates to the various flow models such as Darcy, Forscherman, and Brickman models. Okay, there are different scientists who have proposed different models for porous media, and they are used to describe the flow and convective heat transfer in an enclosure. So porous media finds exhaustive use in the civil and geotechnical fields. Okay, sand, clay, rock studies, and also in the oil exploration, just to name a few, right? And a prominent researcher, Neil and Bejan, both researchers are very famous, have given a review of this works in their article in 2006. Next is magneto-hydrodynamic natural convection in enclosure. So there is another important aspect which is covering natural convection. So natural convection heat transfer of electrically conducting fluids, if you want to see, it is having a great amount of practical importance in fusion reactors. Okay. So we can find it in an article by Morley. Then it is also been extensively used in crystal growth. Dahen et al. In 1996 and 1994 presented this paper, which is directly used in the industrial production of semiconductors and also used in enclosure studies also. Next is natural convection enclosure fluidic nanofluid. So this is the most important. I think the present day world is moving around with this nanofluid. So Choi was a pioneering scientist who presented his article in 1995. He first gave the designated a nanoparticle. So what is nanoparticle? I will not go into the details. It is a different study altogether. Okay, and is just say that is a nanoparticle is suspension of particular maybe silver particles, gold particles, copper particles like that. And when we add that to the basic fluids, the heat transfer gets increased in a mammoth way. Okay, we are not going into the details of how it is happening and all these things, but just I will say that it was first coined by Choi in his article in 1995. So now you see that there are benefits of using particle, nanofluid, and natural convection is that we can get higher heat conduction, we can reduce the pumping power, and extensively it is used in enclosure studies. Next is natural convection enclosure with nanofluid and magneto-hydrodynamic flow. So this is also very much having wide variety of applications in nuclear power plants, appliances dealing with electronic appliances. Okay. Then there is it is having the phenomenon of a magnetic field also, and when magnetic field is there, what is happening is it decreases the rate of heat transfer. So there is a dual play basically. One is actually nanofluid is helping to increase the heat transfer. At the same time, this magnetic field is decreasing the heat transfer. So there is a dual play of both nanofluid and magneto-hydrodynamic, and that makes the study very interesting. Okay. Heat transfer in enclosure in centered body. Now I will come to my present topic. So in a centered body finds direct application in the construction of buildings with a natural cooling flow. Okay. Suppose we are in a room. Okay, we are in a room and there is a adiabatic block placed in a room. How will the heat transfer happen? What will the flow? What is the nature? Just we I've tried to assume that type of a situation in which I have presented this particular
paper. So in such an enclosure configuration, there is a significant core, stagnant core, okay, of the fluid that does not participate in the convection. So that is the adiabatic zone. And in other walls, the side walls, maybe the bottom wall or top wall, which we have heated, okay, maybe given some heat, that results in particular flow of heat by natural convection. So this particular field has also gained recent research significance as a means of heat transfer enhancement. Next slide. Next slide, please. Okay, so here we can find in this slide, there are some articles which have done this type of work. Merrick and Mohammed in 2000, natural convection differentially heated enclosure filled with solid objects. Okay. Then there is Bhave et al. Suggested numerical experiments on optimum adiabatic block size inside a square cavity. Mahapatra studied heat transfer and entropy generation, another aspect of the natural convection. We are not going to the details of entropy generation. That is the second law of entropy, basically. I'm not going to the detail. So he also presented a study, and he proposed a double obstructive blocks. He used double obstructive blocks, square enclosure. And there are basically, we can see there are a lot of studies are there. I'm just limited it to 3 studies. There are several unresolved issues. Now I will come to the why we do this type of work. What is the objective and why do we do? So we have done basically myself have done the literature and found that sorry, there are several unresolved issues which are yet to be answered in regard to natural convection mechanism and block in enclosure, right? And accordingly, we have presented the heat transfer aspects of natural convection flow of a square enclosure with a wavy right wall. Wavy right wall means what? That means it's a wall with basically undulation. Okay, undulation may be a rough wall. We can assume it. So just to understand in a very easy manner, lucid manner. So it is a wall with a roughness. So filled with air, basically, and air has a Prandtl number of 0.71, having a uniform heating and on the bottom wall and adjacent corner, adiabatic square block. So the geometry and the following results can be used for analysis and having a wide range of applications in several collections, which is having wavy wall or wall with surface structures. Next slide, please. Okay, so this is the schematic of the enclosure that we see. So this is a square cavity. On the left hand side, you can see the cold wall. Top is also cold. Right hand side is also cold, but this is the wavy wall that I was speaking of, and this is the equation has been written. So it is given in the next slide. So flow within the cavity resembles basically you can see it is given resembles a 2D view of the room. Is considered as steady, laminar, and incompressible, and the fluid is laminar, and is the fluid is Newtonian also. Okay, all the physical properties are considered to be constant, with the exception of the density in the body force. Next slide. So this is the basically you see that we have directly used the dimensionless parameters, not the dimensional, dimensionless. Okay, you have dimensionless. We have used some group term, dimensionless x, dimensionless y, means the x coordinate, y coordinate, dimensionless velocity, dimensionless temperature, dimensionless other parameters like Rayleigh number, which is the most important part in the natural convection. G beta into th minus tc into L cube minus Prandtl number by mu square, where mu is the coefficient of viscosity and beta is one property of the fluid. Okay, Prandtl number, as I said, thermal diffusivity by momentum diffusivity. Here I have also mentioned Prandtl number. So these are the continuity equations. These are the basically the 2D, the two-dimensional Navier-Stokes equation that we have solved. Energy equation, the Nusselt number, the formula for Nusselt number, the equation of the corrugated wall also, as I was telling, the right hand side corrugated wall, and this is the boundary conditions of the bottom and cold wall that has been put. Okay, so this is the bottom of the cold one. Other walls you can say that is 0, and this is the bottom wall temperature. Non-dimensional, we have converted into dimensionless, non-dimensional. Next slide. Okay, so this is first we go into the study. Before study, we have to do generally whenever a numerical study we do, which is you have to do some validation work. So you have validated our paper. Next, we have validated the our paper by studies from House 1990, Merrick and Leger. So I have put this in the reference also. So this is validation was done. So about the with statistics, you can see the average Nusselt number was validated. The value of the average Nusselt number was tallied for different Rayleigh numbers. So you can see 10 to the power 6, 10 to the power 6, 7 different Rayleigh numbers we have put, and this is the different parameters we have used, thermal conductivity, then solidity also. So the comparison of the average Nusselt shows that the present study is matching with the previous literature. Okay. And here another thing I wanted to say is the governing transport equations are converted into non-dimensional form by using a finite element software, COMSOL multiphysics. This is also another very important slide also, and people must ask what is COMSOL multiphysics, and I want to tell that this is also a very vast area. I will not tell much. I will just say that laws of physics are often expressed in the language of mathematics, and here we are using the conservation laws in such a manner so that the law of conservation of energy that we have said in the earlier slide, energy, conservation of mass, and conservation of momentum, can be expressed in form of partial differential equation. And COMSOL multiphysics is doing the same, and it is using basically the finite element method. There are different strategies by numerical studies. One is the finite volume method, one is the finite difference method, and here in COMSOL we use the finite element method. I will not go into the details, and there is a lot of ways which you, so it will go in pages and means maybe hours together. So I will not just go into the details. So this is the Galerkin weighted finite element method is used to transform the governing equations into system of process. And you can find it in details, the structure. You can find very good books. One I have suggested, Zanesky et al. 1977. So there are several books. Okay, there are several books by which you can learn more about this finite element numerical study. Okay, so basically we divide our complete structure that you have seen, the square structure, into small finite elements, and we solve them into nodes, solve the different non-dimensional parameters at the nodes, maybe at the boundaries. Okay, next slide please. Next slide. Okay, so this is the validation results of the streamline isotherm. That also we can see it has been from the published literature of Habe. That also you can see the upper one is the published literature, and the bottom one we have done by COMSOL multiphysics, that you can see. These are also matching. Okay, that proves that the COMSOL multiphysics is a efficient way by which you can solve our paper. Next please, next slide please. Okay, here the grid independence test, that is also a very important study of this particular numerical study. Whenever any numerical study is done, you have to check the element, which elements you use, how much finite elements you are using, because these finite elements are very important. Because if you are using more finite elements, that means it is taking more amount of time. Also, it is converting more amount of resources, RAM memory. Okay, whatever setup you are using, maybe you are using a laptop, maybe you are using a desktop, maybe you are using any other resource device, you have to use consistently. You have to think of the time and money. So whenever you are using more amount of finite elements, here you see you are basically going in for more finer results, and more finer results mean more accurate analysis. But obviously you have to compensate that with the amount of cost and time. So here we present our studies with 11,300. Why? Because you see that when you increase the number of elements from 11,300 to 28,010, that means there is no remarkable change of average Nusselt number that you can see. So that's why you adopt this particular finite elements, and we proceed with our discussions. So this is the grid independence. It is called the grid independency test. Next slide. So okay, here we are. So you can see that the left one, red ones are the isotherm plots, is the non-dimensional plots, and basically on the right hand side that you can see, this is the basically the very important. This is a streamline. So these are streamlines, and isotherms are one ways of by which you can represent the heat transfer. And it is very important that you know any heat transfer scientist or any heat transfer people, he has to know more about this in detail. So on the left hand side, you see the upper one is for the lower Rayleigh number, and the middle one is for this Ra 10 to the power 4, and on the bottom we have for Ra 10 to the power 5, and on the right hand side you have presented for Ra 10 to the power 6. So as you see, you are increasing the values of the Rayleigh number, which is the main criteria for solving for this natural convection. So as they increase the Rayleigh number, the heat transfer is getting changed. Here you can see the lines are very uniform in case of A on the top hand side. Okay, the value of the streamline values are also very less. Okay, And here, as we increase the value of Rayleigh number, we are seeing that they are increasing. So very interesting, no? So we are getting an increasing. So the flow circulation is also changing. The isotherm plots are also getting more means spreading all over the enclosure. Also, the lines are also getting twisted. So that means, what does it signify? It signifies that there is a convection in the enclosure. In the A cases, there is conduction. There is not much of amount of heat transfer that is happening. But as we move along, means as we increase the values of the Rayleigh number, the heat transfer parameters is getting increased inside the enclosure, and we are left with the situation where we can see in the case of Ra 10 to the power 6, there is a huge amount of analysis of this. The streamlines also have got increased. The value of the streamline value is also getting increased. Here I cannot actually zoom it to tell you about the actual value of, but if you can see the slide, actually it is the value is around 100 and 200. So in that range, so basically it is getting changed. Okay. So, and also you can see that the isotherm plots, the left hand side plots are also getting very much modified. Okay. So next slide, please. So this is isotherms and streamlines by which you can express it. Another way of expressing the heat transfer is by you can see the that local Nusselt number. So local Nusselt number, as I pointed out, that is a very important formula which also heat transfer can be expressed by heat transfer analysts and scientists and researchers, okay, and professors. So here for the local Nusselt number for different wall positions we have placed. So on the top is top left, bottom wall. For top right is the top wall. Bottom left is the left wall, and bottom right is the right wall. So you can see only on the bottom wall the values are all positive. Okay, and it is maximum for this particular green line, which signifies means for what? Which signifies that means it is for Ra 10 to the power 6. So as the value of Ra is increasing, the values of the average Nusselt numbers are increasing. Here on the x direction, it is the dimensionless distance of the enclosure, and on the right y direction, we have the values of the Nusselt number, okay, a local Nusselt. And for the other walls, you see all are negative. Okay, why? Because they are the cold walls, no? So here in this case, the heat transfer is occurring from the fluid to the walls. But here in this case, the heat transfer is occurring from the wall to the fluid, just the reverse. Okay. So next slide, please. Now the average Nusselt numbers are put. There are different situations. So here it is without block. Do cases for block for bottom wall I have given. So now NUB without the second column, third column.
1 more minute, sir.
Okay, sir. Okay, madam. So it is over actually. So this is you can see that without block the values are more. The with block, that means what do our study finally conclude? It concludes that with block the values of average Nusselt number are decreasing. And you can see that all the values for other values are also negative. Okay, what does it mean? This is also, as I said, that is the cold wall. So for cold wall, obviously the values will decrease and they are negative. Next slide. So these are the final conclusions. So natural convection and square conclosure filled with air has been studied. Numerical and square cavity by the very famous COMSOL multiphysics, which is a very important software. Many scientists are using that extensively all over the world. So it is a description of law of physics for space and time dependent problems are usually expressed in terms of partial differential equation, and COMSOL multiphysics using the finite element in a small, very gist manner I have expressed. Okay, it needs to be elaborated in a very large manner. So nature of isotherms have a pattern of shifting towards the left cold wall, and this tendency is more for higher Ra number, the increase of natural convection. So that means the fluid is getting the value of the average Nusselt number, or the convection effects are increasing with the value of the Ra number. And the maximum value of the magnitude of xi, that is the streamline value, you can see it is 100, and it is plus means anti-clockwise orientation. It is moving in anti-clockwise, so it is round and round. It is anti-clockwise wise, it is movement, and it is especially at higher for higher values of Nusselt number. That means for larger convection. Local Nusselt number also shows an increasing decreasing trend maximum because of the imposed temperature gradient that we have put on the bottom wall. And the future studies we can confine to the same enclosure, maybe just a 2-dimensional room, or we can extend it into a 3-dimensional, okay, 3D way. But in the finite elements, you will get change. So you have used a square element or triangular element. In that, it will be a different type of element you have to choose. Okay. Considering porous enclosure, I have said that is very much enclosed in the civil engineering, and it can be considered with nanofluids or without nanofluids, and can be considered with radiation, with the effect of the sun, or EHDS means is the electrical heat transfer parameter. This is also very important aspect of the things. Okay, the next slide. Next slide. Okay, so these are the important references and some papers I have published on this already. They are quite, they have been cited. A lot of them have cited to a large extent. Around 50, 60 citations I've got in 1 to 2 years time. So they are quite read by many people from all over the world. Thank you so much. So next slide.
Okay, thank you, sir, for your wonderful presentation. Now, I would like to request the audience, if you have any query, please,
Yes,
you
please.
can ask.
Yeah, Dr. Santanu.
Yes, please. Yes, sir. Please tell me.
Yes. Yeah, where we are looking where we are seeing the application of this particular thing, the natural convection.
In the second slide, if you see, you just go to the second slide. So if you see the number fifth slide, I have told it, the flow within the cavity which resembles a 2D view of the room. So basically here I have told that natural convection flows are very, very popular. Means for the last 4 or 5 decades, they are being solved. But what is new? Then you can say, sir, what is new in this particular? It is already been solved. But actually, I told you that there are very many unresolved issues. Okay, you just think about if you go to the slide number 5, someone can present the slide number 5. Slide number 5, please. Yes, this one. So here you can see in the bottom I have written, which resembles a 2D view of the room. So suppose you have kept a, this is you are entering a room, and one of the walls is wavy, means the wall is actually corrugated. Okay, it can be corrugated. So I have told, given the equation of this corrugated wall also. You just think that about a room which you have entered, and we have placed a circular block inside this particular room, and the block is adiabatic, means it is sealed from the outside influence. No heat is able to enter inside that body, and no heat is able to go outside that. So this basically resembles a flow inside the cavity, and it is considered. And someone go to the previous slide. Previous slide. Here you can see. So in the last line I have written, last sentence. This geometry and the following results can be used for analysis and have a wide range of applications in solar collectors and electronic devices, as well as the heating and ventilation in buildings with wavy walls or walls with surface roughness. So these are the applications, sir.
Yeah, that's right. So can we think of having this application into the miniature electronics?
Obviously, sir. Obviously, there is a different study altogether. Means my guide and my guide's guide, they are Bhatnagar persons. They have got the Shanti Swarup Bhatnagar award, and they are working in IIT in professor as a regular professor.
My question is that if we are applying your natural convection this thing into the electronics cooling, will it be able to help? Will it be able to help in cooling the battery of the electric vehicle?
Yes, sir. So they have opened up a microfluidic lab just to study on these different aspects, sir.
Sir, please understand, I am just asking a simple question. Will it be able to help us out in cooling the battery which is there in the electric vehicle? Because you have seen the fire catching up into the scooter and the electric vehicle.
So that is another question. Good question, sir. Thank you for asking this question. But first of all, you have to understand what is natural convection and what is forced convection. So
I know that natural convection, will it be able to help, or we should go for the liquid convection?
Yes, sir.
Or should we go for the liquid cooling rather than air cooling?
Sir, if you when you are running a vehicle, you have to think of faster cooling. Okay. So practically, I am saying, sir, when you are running a vehicle, you cannot have to wait when your air will cool and what this thing and what not. Sometimes we have to be a little bit means you have to compensate on the cost, right, sir? So when you are we are running a vehicle, we have to go in for the best possible safety. We cannot compensate for that. So obviously in a smaller domain, when the speeds are less, when it is a very lot of wind is there and all these things are there, then obviously we can go for natural convection studies, no problem. But when you are driving in a very polluted city, then definitely I will whatever you suggested, sir, that is the most important application, right, sir? So you definitely have to go in for some faster cooling, like liquid
Okay,
cooling.
thank you.
Any more
Any
questions?
other question, sir?
Any other
Dr.
questions?
Dotto,
Yes, sir, please.
I have a question. Very
Please.
good presentation and very good, very informative also.
Thank you, sir.
Suppose you are working in a site,
Yes, sir. Please, sir.
construction site. Normally, that office room is top of the room is asbestos sheet and all that. And
Yes, sir.
during daytime, especially in summer, it becomes very difficult to sit inside the room unless and until it is air conditioned or something like that.
Yes, sir.
So can something be done on this area?
Sir, sir, you have put a good question, sir. I want to tell you, sir, I have been means one of my paper is there on this particular wavy wall asbestos room, and it has been shortlisted for a patent from Australian government. Okay. I will share you my paper, and very means they are approaching, the government has Australian council have approached me for this. Was the first paper I presented, because one thing I want to say, sir, whenever the heating is coming on the top, no sir, then you cannot actually apply the natural convection. Means natural convection means when the bottom wall is heated, the heating goes from the bottom to the core. That way we know everything. But if you heat from the top wall, the heat transfer, we do not actually go in for that type of studies. But it is a real life problem that everyone faces. And one of my papers I have presented in such a thing that I have demonstrated how this type of thing can be done with the help of natural convection. We took around 2 years time to solve that paper. And presently it has been shortlisted for this for a means I have not yet approached that government body of Australia. But I want to tell you, sir, there are not many works on this particular area, and it needs to be looked into that matter. And it is a very burning topic, as you have pointed, is a very burning topic, because as the heating is on the top floor, on the top wall, it is a wavy wall, okay, and so natural convection effects cannot be felt very much, only because of the undulation of the top wall. If you understand, sir, undulation of the top wall is the only parameter where the heat transfer is actually happening. But if you heat from the bottom wall, that hot air will move from the bottom wall to the cold wall very fast.
It goes on the higher side.
Very fast, but it is not the other way around. So it is already the top wall is heated and bottom wall is cold. How will the natural convection happen? So that means you have to use some forced convection. But our paper was from natural convection, and we have demonstrated our paper. It is published in Wiley, the American Wiley journal. From that, they have contacted us. We didn't contact them. They had only searched it in ResearchGate was given, and they have recently approached us. It is an interesting study, no doubt, and we want to do some other work, means experimental work. So experimental works will again be a lot of costing is there, and I have approached my guides who are there in professors of IIT. But I basically working in elite college, that is not possible for me right now, so you can understand, because you have to set up the experimental work lab, then we have to simulate a situation which resembles a real life situation. This is not very easy. You are telling it numerically, we can do it very fast, right? But frankly speaking, sir, you understand that it is not very easy to do experimental work of that sort. Because
Professor Dotto, I have one question. That is, suppose you are working in a thermal power plant or a steel plant, around blast furnace or boiler.
Yes, sir.
There, these sort of things can be applied.
Yes, sir. Obviously, they can be 100%. They can be applied everywhere.
Because ambience around those areas are very bad.
Yes, sir.
You work in a steel plant in around blast furnace or in a power plant around that boiler. It is really a very tough thing.
West Bengal government, sir. It is West Bengal Power Development Corporation. You may be heard of that particular company. We PDCL. I worked for 8 years there. Means in the boiler area, and in the later I shifted to a turbine area. When a
Okay.
boiler area means I was getting scorching hits, means all my hair, receding hair line, everything. Means I got older, means by 4 or 5 to 10 years working in that particular zone. All my hair fell off. Means there's a very horrible experience. And later, then I decided to I'll shift it to means means
Academics. Okay. Okay. Thank you, Mr. Dotto.
Thank you.
For your
Okay.
nice
Any
Okay.
other
presentation.
question from any means from students, or I tried my level best to make it as simple as possible.
Okay. Okay. Thank you, Dr. Shantanu Datta sir. So moving to the next contributory presentation. Our third contributory paper is a student paper, and it is on the Johnson walking robot, authored by Maul Haq, Akash Nandi, Arun Kumar Nandi. I would like to call upon the presenter, Maul Haq, to start the presentation.
Yes, sir. Yes, ma'am.
Okay, please try to finish it within 10 minutes. Okay, so we are running short of time already. Okay.
Okay, ma'am. Sure.
Okay.
Okay, ma'am, and sir, good afternoon. Good afternoon, everyone. My name is Maulok from Elite College of Engineering, a last year mechanical engineering student in 2020. So today I like to share this presentation about my paper. But first of all, I like to thanks to this uh, Development in Engineering Education and Practice 2022 for letting me share the thoughts and giving us a wonderful platform to share our thoughts in a national level. Uh, I also like to give a huge thanks to our director of our college, our principal, our head of the department, and all of our members who have helped us for this paper and encourage us in every steps from beginning to till end. So let me start my presentation. Okay. 2000, yeah, this is the one. Is it visible? No?
This getting, just wait for a sec. Make it
Okay.
full screen.
Yeah. Is it
Okay, okay.
okay?
It's done.
Okay. Okay. This is a idea and our thoughts regarding this PPT presentation, a Theo Johnson mechanism. This is myself, Paul Hope, and uh, let's start with the mechanism. What is this and what all of this about? Actually, the Theo Johnson mechanism is designed by the scientist Theodorus Gerardus Joseph Johnson. This is a particular mechanism actually for leg robotics. He has designed this as an artistic way, and our thought is to make this art in a very unique way in practical world. After researching a lot about this project, I have I have found that this is very energy efficient, bio-inspired locomotion, and very unique way to do such things in that has not been accomplished by various field. Let me explain what is this all about. So our object is to develop and engineer a mechanism in our real world situation for multiple application, multiple purpose. So our goal is this. This mechanism can do many things, like it can carry loads, and it can replace certain limitations from wheels, like wheels are used in lot of situations, but there are like some places like rocky surfaces or inclined sandy surfaces where wheels are very hard to get. This our mechanism can accomplish those hurdles very easily. And if we add advanced robotics in this mechanism, then we can accomplish various other tasks, like let's say there's a fire in fourth floor. So our mechanism has a certain that ability to climb stairs, or if we implement such mode other stuffs, we can add there you can see there's a green platform. We can add a automatic fire extinguisher switch that is triggered by using heat or by using cameras sensors. If a fire took place in fourth floor, the mechanism will automatically climb on that place and distinguish the fire while the fire brigade members comes, because in India there are lots of places fire brigade members came a bit late because of traffic jams and those. So these mechanisms are applied in various apartments or buildings already previously installed. We can achieve this. So we can do much more than this. We can use in military uses, we can do rescue operations, we can also work on space missions, because because we know in space missions there are very rocky surfaces or inclined surfaces, or like lunar crates in moon, or various crates where wheels are very hard to climb on those surface. So our mechanism can overcome those situations, and our mechanism has a limitation, like we can climb up to 45 degrees of inclination. So this is an example that I have found. This is a very interesting example, that this entire body is almost 2 ton, and the person is pulling the entire mechanism by a single rope. I found this in the YouTube, and in the first point I have shown, this can carry weights, so we can use as a carry huge weights, and as it is a very energy efficient mechanism, we can do such things. So our applications of our project is stair climbing in rescue operations, military uses. In military uses, we can use in various autonomous defenses, surgical strikes, or even simple things like patrolling in rural areas where people are hard to get, or in various small places by using IoT, Internet of Things, and in space missions also. Over climbing the inability to climb inclined surfaces, we can do up to 45 degrees, or in rocky places in various space missions. So the methodology of this is actually is very unique. You can see this is a wheel motion, and the path of the wheel is going like this, and the Theo-Johnson mechanism is going like this. So actually uh, for move, a basic concept to move a object is, if there is a zero relative velocity with the surface, then the object will move. But if there is non-zero relative velocity, then the object will slip. So for a wheel to move a body, the wheel have to have a relative velocity with the road. For that reason, the point of contact uh, uh, have to be done in each point of the wheel, which increases the frictional resistance. But in Theo-Johnson mechanism, the point of contact has been done in some places. You can see the point of contact is this, but when the movement is going backwards, the point of contact with the road is non-zero. And for that reason, Theo-Johnson mechanism's frictional resistance is low. And if the frictional resistance is low, then the total output energy we can get is high. And as the output energy we can get high, we know because of the torque is equal to Fr cos theta, force we are getting higher, then the torque is also we are getting higher. But it has a drawback that Theo-Johnson mechanism only can move lesser distance than wheel. In this area, you can see the direct comparison of those two parts. Theo-Johnson mechanism is slow because the distance L is low, because the forward movement is lesser than the wheel, but it has a higher energy efficiency. So this is a design prototype that we have made in AutoCAD. This is all of the parts our in our mechanism, and we have imported that AutoCAD design in our SolidWorks, and we have assembled This is a single leg piece design. This is the crank which has been used, and this is what I have made in using ice cream sticks to make such a prototype. And this is the dimension of a single leg prototype, and this is a third angle view of our fusion mechanism in SolidWorks. We have made a basic design in our SolidWorks. This is the SolidWorks simulation, and this is what we have done in our college life. A prototype has been made in the right part. So this is the calculation that we have gained, and I don't think we have that much of time to explain the entire
Yes,
calculation.
Maul,
Yeah,
you have only 1 minute left. Okay,
yeah.
please
Okay,
conclude.
okay. In brief, I can say that we have calculated linear torque and power calculation. We are getting 67 watts of output power, and while in angular torque we are getting almost 1300 watts of power. So in conclusion, I can say that scientist Theo Johnson make this as an artistic piece, and we are trying to make this in a practical world that can be used in various things, and that can be open various new fields. Like we can in the major things we can do is like carrying heavy weights or overcoming limitation of wheels, climb stairs, military use, IoT in robotics, and many more. And in minor things, we're also love to share this idea to various R&Ds, to do various research on this design, that we can accomplish these things. And if we add various machine learning and AI, we believe we can achieve a huge success to overcome various limitations on this mechanism, using these mechanisms. So thank you. If you have any questions, I'm open to share.
Okay. Thank you, Maul, for your wonderful presentation. Now, I would like to request the audience, if you have any query, please raise your hand, or you can write it in chat box also. Yes, Dr. Ashwini Kumar Sharma, sir, please.
Yeah,
ahead.
Maul.
Yes, sir.
Yeah, this project is completed.
Yes, we have made a SolidWorks simulation, and
No, the physical prototype.
a basic physical prototype has been made during our
Okay.
college life.
Okay, you have already done that. So why are you working still on it, or you have left it?
We actually worked on that thing while we are at college, but after that, sir, because we're looking for other stuffs also. But we are working
Okay.
on this research paper, on this
No,
paper.
that is right. That is right. And what was? Have you participated somewhere with this?
Uh, no, this is the first time I'm sharing this idea to a national level conference.
Okay. That's okay. Fine. Thank you.
Okay, thank you, sir.
Thank you, sir.
Dr. Ace Banerjee, sir, over to
Yes,
you, sir.
Maul,
Please.
the very good project I have seen. So you could have availed the opportunity of Knockout. They are also giving, making this sort of presentations and projects. They are encouraging also. They have some sessions every year. So you can go for that also, for your first prototype, rather presentation or something like that. Anyway, you are working on this, or you have left?
No, sir. I am just roughly working on this, but I would love to work full time on this also. But I'm right now working in a company also.
And now you are working where? In a company means, is it a software company or
Yeah, in a IT based company.
IT based company? Okay.
Because of the money issue, we in our family, but that's why I have to work right now. Otherwise, I love to
Don't
work.
give up. Don't give up this initiative, okay? Because it might take you to a different level in future. I hope so. And so you must do not leave this thing just as it is. You
Okay,
are
sir.
working where that is fine because of family constraints and all that, but you should not leave these sort of things. Okay. Thank
Okay,
you very
sir.
much for your presentation.
Thank you so much, sir. Thank.
Okay. Okay.
Thank you, sir, for your inspiring words. Thank you, sir. Now, I thank you, Maul, for your wonderful presentation. Now, I'd like to move to the last presentation of this session. Fourth contributory paper is on behavior of stress-strain relationship of few metals by Shouvik Saha, Rakesh Kumar, Sudeep Basak, Gaurav Ganguly, Krishna Hazra. Now, I would like to request our Honorable Principal Sir, Professor Dr. Sudeep Basak, to start his session. Over to you, sir. Thank you.
Okay. Thank you, Professor Deepasri Shah. So, am I clearly audible and visible?
Yes, sir. Yes, sir. You are
Okay. Thank you
perfectly
very
audible
much.
and visible.
Thank you. So, I will try to start my slideshow if it is
Yes, sir.
visible.
Sir,
So, please.
one thing, sir, you have just 10 minutes.
Oh,
Please,
yes.
you
Sure,
have
sure,
to
sure.
finish,
I
please.
will limit myself within the time limit. Right.
Yes, sir. Yes, sir.
So, let me first share my screen and let me know whether it is coming. Is it coming?
Sir, it is coming.
It is not full screen, right?
No, it is not full screen.
So,
Yes,
is
it
it?
is now. Is it? I think it is full screen now.
Yeah. Okay.
Yes.
So, you must be feeling very hungry during the lunchtime, all of us, including myself. Uh, but still, I will manage to finish as early as possible within the given time limit of 10 minutes. Actually, this project is based on tension test of metals in plastic zone, right? By my students have done their project and they are already passed out. So I requested them to come and give a presentation. You no need to come back to college. You give presentation in virtual mode, but unfortunately all of them are busy with their job, so it is only me who have to present, their project supervisor. So it is basically a tension test of metals in plastic zone. So we all know that the what is the tensile or what is the stress strain characteristics of metal in elastic zone, but the knowledge on plastic analysis is still improving. So that is basic motivation of this work. So you know what is a tension test. All of us know it very well, right from the our undergraduate studies. So it is a fundamental test in material science, and which is commonly used for quality control, right? And metal specimen with standardized geometry is being tested in this test, and the specimen are subjected to uniaxial tension till the failure takes place. So it is basically a destructive type of test, uh, as which was first given by Davis 2004. You have some literatures, and commonly the properties which are determined, properties of the metals which are determined are basically the elastic limit, the Young's modulus, the yield stress, the ultimate stress, and the Poisson's ratio. So these properties are required to design uh, for design purpose of a project, basically. So let us first try to understand what is the stress strain response, standard stress strain response of a material, of a metal, right? So in the x-axis, you can see the strain, okay? So it is strain is nothing but the elongation divided by the initial length. And the y-axis, it represents the stress. So this stress is actually the nominal stress. I will come into the details of this parameter. Nominal stress is the applied load divided by the initial cross section area, right? So basically this the basic variation is like this. Whenever we apply some uniaxial tension, right? So initially linear increase between the stress and strain up to the up certain point, and this point up to the point of linearity, it is called the proportional limit. That means the stress is proportional to the strain up to this point. So beyond this point, whenever extra additional load is applied, right? So the elastic limit takes place, right? So the proportional limit or an elastic limit are something different. So between these 2 points, the material exhibits non-linear characteristics. Okay, the proportionality between the stress and strain are not valid beyond the proportional limit, right? So in some metals, these 2 points coincides, and in some metals they don't coincide, right? So the elastic range, this is the elastic region, you can see in the graph, elastic region. So at any point in the elastic region, if you withdraw the imposed loading, what happens? It drops down to the original point. So no residual stress is, no residual strain or no residual deformation is left in the material being tested, right? So that is the speciality of the elastic region, and that is in fact the definition of elasticity. Whenever we withdraw the load, it regains its initial configuration, right? So beyond this elastic limit, so if you further apply the load, yielding starts in the metal. So what is yielding? Significant increase in the strain or the elongation without significant increase in the stress level, right? So that is called yielding. The stress level increases marginally compared to the increase in strain level. That is called yielding of material. Okay, we have lower yield point, upper yield point, something like this. So we have all learned it in our undergraduate studies. So after that, there is a strain hardening zone. So what is strain hardening zone? So in this zone, there is a much increase in, compared to the yielding zone, there is much increase in the applied stress level, and there is also increase in the strain level, right? And till the maximum ultimate stress is developed, this is the ultimate stress. Okay, and at this point the neck formation start in the specimen, the necking starts. Okay, so as soon as the necking starts, the plastic flow of metals takes place, and there is an acceleration in the gripping, and the gripping of the test apparatus, the gripping, there is an acceleration takes place, due to which there is a apparent reduction in this stress level. Okay, and at this final point, this is a necking zone, and at this final point, complete rupture of the material takes place, right? So the next formation, this one specimen has now become two specimens. They teared apart into two specimens. So this is the specific stress strain variation, a typical stress strain variation of metals, right? So different metals show different characteristics, and ductility and brittleness is basically is a function of the work done. So work done per unit volume is basically the area under this graph. So significant, the more is the area, the more is the ductility. It is said in the theory of plasticity, right? So let us go to the next slide. So yes, this is the apparent stress and true stress. Okay, you take a specimen, initial AD cross-sectional area, initial length is L, and small l is the elongation, and A is the fine reduced cross-sectional area, right? So you apply a uniaxial tension F on the specimen, right? So the apparent stress, as we have just said, it is the tensile force applied divided by the initial cross-sectional area, the F by A0. But that is not the actual stress. Why? Because the cross-section is progressively reduced. Okay, so the true stress, sigma T. What is true stress? It is the tensile force divided by current cross-sectional area. That is F by A, not F by A0. It is F by A. And the denominator of the next term, A0L by L plus small l, capital L plus small l, actually it comes from the volumetric constancy. Okay, so whenever there is a increase in length and decrease in cross-sectional area, so the volume of the specimen will remain the same. In most metals, it remains the same. So initial volume will be equal to final volume, and from there this expression starts, and it becomes this expression, epsilon A multiplied by 1 plus epsilon, right? So in this way, the true strain is developed, calculated. And engineering strain, as I have discussed, it is the elongation divided by the initial length, and the true strain is logarithm of 1 plus epsilon engineering strain. Okay, 1 plus engineering strain and whole logarithm. That is the true strain. right? So in the left-hand side graph, you see the graph below graph, the bottom graph is the apparent stress strain variation. You can see the reduction, and in the true stress strain, you can see the increase, right? Because the true strain never increase. Because of neck formation, the cross-sectional area is reduced. So apparently it appears that the stress is reduced, but actually the stress is not reduced. The true stress is indeed increasing, right? So you can see different zones here: the ultimate strength, yield strength, rupture, strain hardening region, necking region, apparent stress, and actual stress, right? So we have already discussed this. Let us now go to the next slide. So some definitions: the elastic, plastic, and tangent moduli, right? So this is the left-hand side graph is true stress versus the true strain, right? So initially there is an linear increase, after that non-linear increase. Okay, so in the linear zone, the slope of the curve is elastic modulus, or we can say it as Young's modulus of the material, right? And this is the elastic limit. You can see the elastic limit, and at a certain point A, let us take a point A in the non-linear zone. Okay, and take a tangent here. The slope of this tangent, okay, is called the tangent modulus. Okay, and it is not shown here. If you join this point A with the origin, and the tangent slope of that straight line is called secant modulus. Okay, it is not shown here because I think it is not required by the students. So in the second portion, it is the true stress versus the plastic strain. What is the plastic strain? So if you take a point in the elastic zone, okay, the strain developed is completely elastic. That means whenever we withdraw the loading, it regains its original configuration and the strain is zero, right? But at the plastic zone, the nonlinear zone at a point A, if you withdraw the external loading, it does not regain its initial configuration. Some residual strain is left, some residual elongation is left in the specimen, and that is the residual elongation. Okay, so the strain is composed of elastic component and the plastic component. Okay, so the plastic component is the total strain minus the elastic component, right? So we have plotted in the next graph the true stress versus the plastic strain, right? And in the plastic strain, this is the point A. Okay, the same stress level as this, the point A. If you draw a tangent, that is called the plastic modulus H, right? And from the theory of plasticity, we can easily derive this equation: 1 by T equals to 1 by E plus 1 by H. Okay. So this equation is required for design purpose later on. Okay. So as we know, the Poisson's ratio, it is not correctly written here. Actually, it is minus sign comes here. So it is the ratio of lateral strain divided by longitudinal strain within elastic limit. That is the true definition. So sometimes when I ask students in the class, what is Poisson's ratio? They said lateral strain divided by longitudinal strain. It is not like that. Within elastic limit, the magnitude of lateral strain divided by the magnitude of longitudinal strain, that is the true definition of Poisson's ratio, mu, right? Because the lateral
Sorry to interrupt, sir. Sorry to
Okay.
interrupt.
Right.
Sir.
1 minute left, right?
Yes, sir. Yes. Sir.
Right. Okay, let me finish within 1 minute. So contraction ratio is beyond elastic limit, the ratio of magnitude of lateral strain by longitudinal strain. That is the contraction ratio, not the Poisson's ratio. Okay. And from plasticity theory, we have derived this equation. We have not derived. It is in the theory itself. So eta and mu. Okay. So there are various tensile testing machines which have their own merits and demerits. First comes the universal testing machine. Okay. Next comes the mechanical testing machine, and third comes the Hounsfield testing machine, tensiometer, right? So it is a manually controlled, the third one, and other one is mechanically controlled. The first two ones are sophisticated, and third one is manual, right? So our students did this manual testing very easily. We have several components here, and the graph is easily plotted. So you rotate the handle and the graph is plotted. Okay, feed the specimen, rotate the handle, graph is plotted, and the specimen is tear up. So this is the specimen. This is the grip section. and gradually tapered to the gauge length, right? So this is the load versus elongation. We tested three materials: mild steel, brass, and aluminum, and from which these are the computed results. We computed some parameters: mild steel, brass, and aluminum, and this is the true stress strain curve we plotted: mild steel, brass, and aluminum, and the tangent modulus we derived from these curves. They are non-linear pattern, so also the plastic modulus, right? And what is the significance of this study, right? Ascertaining the comparative behavior of metals in the plastic zone under uniaxial tension. This is the first basic significance. Information of the true stress strain characteristics and plastic pattern of variation of tangent and plastic modulus of different metals. And the third one is acquiring knowledge of the extent of plastic zone and the associated test of state of stress in terms of plastic work done and resilience. And the last one is that the uniaxial tensile test results can be utilized for plastic analysis of structural components under complex state of stresses. This is the engineering significance, right? So the work is still going on, and one of my faculty members, Mr. Pallav Sarkar, who is working on it, and some student project is under progress, and they will give some important results, interesting results. So thank you very much for your patience hearing, and I think all of us are hungry for lunch, and we are already running shortage of time. So I finish here. Thank you very much.
Okay, thank you so much, sir, for your wonderful presentation. Now, I would like to request the audience, if you have any query, you can raise your hand or write it in chat box, but keep this short. Okay.
Sir, I have one question, sir.
Okay,
Yes, please.
Sir, were there any experimental work done? As far as I remember, there was some experimental work done in this paper. So you didn't present some experimental work that you
Yes,
did.
basically this work is basically this is a pure experimental work without any theoretical deliberations.
That
Purely
only
experimental. Yes, yes. If you go to the slides, you can see that it is purely an experimental work. That is, we tested the specimen, three specimen in this apparatus, and we got these results. Okay, load versus
Yeah.
elongation, and we computed them and find the further results. Right.
Actually, you didn't present this. That's
Yes,
why
because of shortage of time.
I understand.
Yes, yes.
Okay. So anyone else, judges, if you have any query?
No, ma'am, my side done.
Oh, okay, okay. Thank you so much. Okay.
Thank you, Professor Borshak, for your beautiful presentation, and we really enjoyed the session.
Thank you
Nothing
very
else to ask. Thank you.
Thank you so much, sir, for your valuable presentation. Okay, now we are at the end of this session. Now I would like to request our session chair, Professor Dr. B.G. Gupta, sir, to kindly wrap up the session. Sir, you are not audible. B.G. Gupta, sir. Professor B.G. Gupta, sir, you are not audible. I would like. Yes, yes. You are now audible. No, sir. Still now we are not hearing you. I would like to request the wave host. Please check.
Okay.
Yes, sir. You are now audible.
It's okay.
Yes, sir. Yes, sir. But sir, your camera is on the rear front, I think so. Your face is not visible. One thing I should mention, thank you, judges, for your precious and valuable comments. Actually, we are running short of time, I would
Hello.
like to request Videsha
Hello.
sir.
Hello.
Yes, sir. Yes, sir. You are audible. You
Okay.
are audible.
I a special thank to our distinct committee, Deep 2020 committee, and our director and principal sir for giving me an opportunity to present to be the chair of this session. And today, in this the first session in the mechanical engineering, we have a nice presentation of Dr. A.K. Khatua, Dr. P.K. Khatua on his paper consolidation of materials. And thereafter, this presentation of papers of the teachers and students as well. The first paper was this multi-purpose wheelchair, which is presented by Vishwarup Poddar, who is the ex-student of this institution. Second, this yeah, woman Santanu Dotto, who is the associate professor of this college of mechanical engineering on the influence of thermal boundary conditions on natural convection heat exchange transfer in a wavy wall square cavity with adiabatic rock. And the third one is again by the student of this college, Mohul Hawk, on Theo Johnson mechanism, and again by the students, which is been presented by our principal, Sudeep Posak, on tension test of metals in plastic zone. So all the papers are nice, and this informative. I will specially thanks to Dr. A.K. Sharma and Dr. S. Banerjee for the present hearing for last 3 days and working hard for this conference. And a special thanks to Subhashi Bandyopadhyay, Banerjee and Dr. A.K. Sharma for their this contribution to this particular conference. So I am not taking much more time more, and I just wrap up the session right now. And welcome everybody for going to their lunch for again coming back on this next section. Thank you.
Oh, okay. Thank you, sir. Thank you, sir, for your concluding remarks. So now I would like to thank the audience. Okay. We okay. After 30 minutes lunch break, we will meet at 2:10 p.m. for our next and last technical session 5. So there is an echo. Okay, now this is perfect. Thank you, audience, for your patient hearing. Please join us at 2:15 p.m. for next technical session 5. Till then, enjoy your lunch and have good time. Thank you. Okay.